Okay, this is the video that was requested. The notes I got looks like call by reference, call by value, and malloc. I'm not sure that's everything I was supposed to do, but I'll do that and we'll see what comes back. I've been told in my videos I look unusually orange. I guess that's when the sun's out, and now I look unusually white because I'm lit from above. Okay, so here we go. I'll call this call by. And so I'm going to make variables called x1 and x2. And I'll make a function call by value. And I could make this really confusing and give it a name like x1 or x2, and I'm not going to do that. So let's call it x3, and another one called call by reference. And when you're calling by reference, you don't pass in a value like an int x3, you pass in a pointer like x4. So if I set x3 to 3 and x4 to 4, now that won't set x4 to 4 because x4 is a pointer. And so what I need to do is I need to say the value of x4 should be assigned the value of 4. So 4 should be assigned to be the value of this pointer, x4. And then if I call by value with x1 and call by reference with the address of x2, and then I print them, then what are we going to get? Well, it turns out that this one, x1, is not going to be changed, but this one, x2, is going to be changed. So it's going to print x1 equals 1 and x2 equals 4. So let's see that happen. Okay, so what happened here? I think the easiest way to see what's happening is through pointers. So first off, let's get what the pointer is for x1, so or the memory location for x1. So x1 is at address of x1, and x2 is at the address of x2. Now, when we go up here and say what is x3, and x4, this actually won't really help demystify this. So I'm going to compile this and run it. And it says that x1 is at location BEC, x2 is at location BE8, x3 is at location BBC, and x4 is at location BB8. And so all of them are at their own locations. And part of that is because whenever you have an argument to a function, that argument gets its own memory location, as evidenced by these pointers. So x1 is at memory location BEC, and x3 is at a distinct location, which is the location BBC. And so what's happening here is when we call by value, the value of x1, which is 1, is being copied into the location of x3. And then we assign x3 to have the value 3. So this location right here gets the value 3. And when the function goes away, this memory location goes away. We don't have any right to access it anymore. And then when we go and print what's at x1, well, x1 was never changed. The only thing that was changed was the copy of x1. See, if we go up here and say the value passed into call by value is, it's going to be 1, and here we can say now the value for x3 in CBV, and this will print 1 and 3, but when we get back to the end, we're still going to have a value of 1 because we have a distinct memory location for this variable, and we're passing the value, which is 1. We're copying that value into this variable. This variable starts with 1, it gets changed to 3, but then it just goes away. Poof, it's gone. And then when we go back to x1, nothing has changed. So here we see that BEC, the value being passed into call by value is 1. X3 is at still BBC. And then after we're done writing, it's 3. But then this whole memory location right here goes away. And then when we print x1, nothing has changed. So that in and of itself isn't hopefully too hard to understand. But then what's weird is this one doesn't work the same way, that we're passing in x2 and yet x2 is modified. And the reason why is because it's called by reference. So the big trick of this one is we're passing in a pointer. And you see right here, there's 2 pointers in play. I have printed this. This is an integer. It has a memory location. This is another variable. It occupies 8 bytes. And I printed out the 8 bytes that this pointer occupies. There's a separate question of what does it point at? Well, x4 is going to point to, so you see it's the difference between the address of x4 and this would print the pointer, the location that x4 is pointing at. So let's print that out because that's going to be important to this conversation. Oops. Ha 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 ha. There we go. So what's happening is x2 is BE8, x4, just in the same way that x3 was a distinct memory location from x1, x4 is a distinct memory location from x2, and it better be because it's a different type. So this type takes only 4 bytes, and this type takes 8 bytes. So the 8 bytes that are required to store the value of x4 are at BB8. But the question is, what's in this location? What's in the location is BE8, the location of x2. And so what's being passed in, so we could do yet another one. We could say the value passed into call by reference is %d, and then we can do this. So you see we have a variable x4, it's a pointer. The address of this pointer is just the address where the pointer is being stored. The value of the pointer, well, and then the pointer is pointing to this location, which is the location of x2. And then the value at that location is going to be an integer. So you see we're printing a pointer, and an integer. And so then we'll do the same thing as we did here. And if we compile this, whoops. If we compile this and run it, then we can see that the value passed in is 2, but we're setting it to 4, and that 4 takes hold. And the reason it takes hold is because we're actually taking the real memory location here at x2, which is BE8, and we're saying set the value at BE8 to be 4. And so when we return to main, then its value is still 4. Okay, so I actually think making it harder will make this whole thing appear easier. So let's see if I can be right in doing that. So how does this work in practice? If we have an image.c and we have some struct that's an image and it takes a width and a height, and then we've got some function like read image, and we give it a file name and an image pointer. And we go here and say I width equals 1,000 and I height equals 500, and then we print the width and height, then what we're going to get is we're setting the width and height in this function, and it's changing what happens in this function right here. And that's what we'd expect. We expect if we have an image here and we pass in the pointer of this image, and here this function gets a pointer and it makes changes to the data members, that it would affect the image in the calling function. So this is a pattern that actually we're used to and we liked in the context of passing in images, but when we pass in integers, it seems kind of weird to us sometimes. Okay, so one other comment I want to make is, well, let's see, so first we could do this. If we do this, I'm pretty sure bad things are going to happen. So when we did that, we got uninitialized values for width and height. And the reason why is because we went back to doing call by value. And so this is one of the very few times that C will secretly do a lot of work for you. In this case, the lot of work is it's copying the values, the data members of this struct, into a copy, a second struct called image I. And so it copied the values, which were uninitialized memory, and in the second struct, the copy of the image, we put in the right values, and then we threw it away. And then in the new one, we still had our uninitialized memory, 2.8 billion and 1, or maybe 280 million. Okay, so one more thing I want to do here. Oops. And again, now because we've got a pointer to a struct, we'll use an arrow. And so this should be back to good. It's not. Okay, so now we're getting the right thing. So the other thing I wanted to show here is this is putting our image struct on the stack. It's using automatic memory. We could just as well have done this. So this would be making a struct with 8 bytes, 2 ints, and then so as far as mount's concerned, we're just requesting 8 bytes, but then we're choosing to interpret it as a pointer to an image struct. And then we can just do this. And now we're still doing call by reference, but now we're getting a pointer through malloc. Read image is accessing it through the pointer, and so are we. So it's now a little more symmetric. We're both accessing it as a pointer, but we're both using the same pointer. In this case, the pointer that we're sending is actually being copied. We get a second copy of the pointer here, but they both have the same value, and we're both interacting with the same location. And so when we do this, well, we're going to have to add standard lib.h, but when we do this, we still get the right thing because they're both working with the same pointer. And let me just be really clear on that point. The location of pointer I is %p, and the location is the address of that pointer. And then the value of pointer I is I. And similarly, the location of pointer img and so now if we compile this and run it, see our two pointers are at different locations, BE8 and BB0, but they're both pointing to 530. And since they're both pointing to 530, that means they're both pointing to the same object. And let me just prove that too. I can say the location of width is at %p, and then I'd take the location of I width and this would be IMG width. And so here, since width is the first data member, it's got actually the same location as the struct itself. Just change that to height. Actually, let's just do this. Sneaky, sneaky, sneaky. Okay, so now the image pointer itself is at 610, and the width data member is at 614, and again 610 and 614. And so when we're writing to width, we're writing to the location of 614, and when we're reading here, we're reading from location 614. So the write to this location right here is the same as the read right there. And if we were to again do this, well, then we'd have a copy of I, and then if we were to print this width, it wouldn't be the same. I'd have to change not a lot of code to do it, but I think it'd get kind of boring. The punchline would be that the location of width would be different because it'd be the location of the width in the copy. Okay, I hope this has been useful for explaining call by reference and call by value. I'll see you all on Monday. Bye.